Um, Now let's take a look at one example to see how we prove that some problem is NP-complete. Right, so here's, suppose that we already know that the Hamilton cycle problem is NP-complete. Now let's prove that the traveling salesman problem is NP-complete as well. The Hamilton cycle problem is, given a graph G, is there a simple cycle that visits all the vertices? That's the decision version of the Hamilton cycle problem. The traveling salesman problem as TSP is to, given a complete graph with edge costs and an integer k. And the question is there a simple cycle that visits all vertices and has total cost which is less than or equal to k? The original problem is to find, actually, in a complete graph, a Hamilton cycle with minimum cost. Right? This is the decision version of that problem. To prove this, the first thing to do is to prove what? Is to prove that TSP is in NP. This is obviously true because given any simple cycle that visits all vertices, it takes only a linear time to sum up all the costs and compare it with k and to tell yes or no to that question, right? So its answer can be verified polynomially, and therefore TSP is in NP. Then we're going to try to prove that the Hamilton cycle problem can be polynomially reduced to TSP. So we start from any instance in the Hamilton cycle problem. And this is not necessarily a complete graph. The trick we used here is this. We assign 1 to all the edges that are in the Hamilton cycle problem. And then let's make it a complete graph by adding some new edges. And we assign the weight 2 to all those red edges. Those red edges were not in the Hamilton cycle problem, but they are in the traveling salesman problem. Okay? And that takes only polynomial time to do so, right? In the worst case, it's going to be what? N squared, where n is the number of vertices. So now in polynomial time, we can map an instance in the Hamilton cycle problem into another instance in the traveling salesman problem. And in the traveling salesman problem, let's define this k to be equal to the number of vertices. The next, what we're supposed to prove is this. Say, the original graph G has a Hamilton cycle if and only if this complete graph has a traveling salesman tour of total weight being equal to the number of vertices. It's not so hard to prove it, right? Say, if we start from, say, G has a Hamilton cycle, then it means that we do have a simple cycle that visits all the vertices and consisting of only those black edges, and therefore the total cost of that Hamilton cycle is what? It must be equal to V, because each edge has to be black and has the weight 1, and there are totally V edges in the cycle. Okay, so this is true. Now let's prove the other way around. Suppose that this complete graph has a traveling salesman tour of total weight V. It means what? A traveling salesman tour is a simple cycle that visits all the vertices, and therefore it must contain V edges. And the total weight is V. It means that each edge must have the weight 1. It's impossible to have any edge of weight 2. That means this traveling salesman tour must consist of only the black edges, which means that the original graph must have a Hamilton cycle, and that completes the graph. So the logic here is what? Is that we know that Hamilton cycle problem is NP-complete. Therefore, any problem in NP can be polynomially reduced to a Hamilton cycle problem. And we have proved that it takes polynomial time to reduce Hamilton cycle problem into traveling salesman problem. And therefore, any problem in NP can be polynomially reduced to Hamilton cycle problem first, and then in polynomial time reduced to TSP. And therefore, that proves that TSP is NP-complete. So once we know that some problems are NPC, we can prove that some other NP problem is NPC by showing that an NPC problem can be polynomially reduced to this one. But there's ought to be the first one to start with, right? So this is the first one. The first problem that was proven to be NP-complete was the satisfiability problem, also called circuit SAT. The problem is to input a Boolean expression and ask if it has an assignment to the variables that gives the expression a value of 1. For example, a Boolean expression like x and y or z. And obviously 1, 1, 1 is a solution, right? But for an expression with n variables and complicated Boolean relations, the exhaustive search runs in exponential time. It's 2 to the power n, right? Because each variable has 2 possible values. It was proven by Stephen Cook in 1971 that all the problems in NP could be polynomially transformed to satisfiability. And he proved it by solving this problem on a non-deterministic Turing machine in polynomial time. By the way, there's another term called NP-hard. An NP-hard problem is harder since it may not be in NP. That's the difference between NP-hard and NP-complete. Remember that NP is easy to check, but NP-hard problems may not be checked easily. NP-hard is at least as hard as NPC, but probably harder.